Okay, so exact differential equations. You have a differential equation of this form. This set equal to 0. A necessary and sufficient condition to be for this to be exact is the partial derivative of this guy with respect to y equals the partial derivative of this guy with respect to x. Okay. So let's see what's so good about this problem. Okay, so let's start by taking the partial derivative of m with respect to y. So let's do partial derivative of m with respect to y, which will equal the partial derivative with respect to y of 5x plus 4y. Now remember, when doing partial derivatives, the partial derivative with respect to y treats x like a constant. So it's viewing this thing as just being a constant. So this is going to go to 0. And so we're just considering the derivative of 4y with respect to y. Now I'm going to take the partial derivative of m with respect to x. And so that's going to equal the partial derivative with respect to x. This guy right here. So this is going to be 4x minus 8y cubed. Okay. Well, it's going to send this one to 0, but the derivative of 4x with respect to x is 4. Give a check mark.
What do you mean by exact? They're just the same.
They're the same. It means that if you take the partial derivative, it's another, all right, so it's a classification of differential equations. And what this basically means is if we're looking for a general function f, if this is true right here, it means that this thing right here is going to be the partial derivative with respect to x. And this is going to be the partial derivative with respect to y, if this property is true. Okay. So what that means we already have that it's exact. So that means that the partial derivative with respect to x is going to equal 5x plus 4y. Okay. So what I'm going to do to this is I'm going to, that means that f of xy is going to equal now the integral of 5x plus 4y. Okay, and that's going to be an integral with respect to x. And so that's going to turn into 5. Now x squared divided by 2. Now plus 4xy plus some possible g of y. Oh crap, I wrote it down. Okay. Now the partial derivative of f with respect to y is going to equal to the other one. So that's 4x is 8y cubed. And so that means that my f of xy is going to equal the integral of 4x minus 8y cubed with respect to y. Now the integral of 4x with respect to y would be 4xy. Okay? And now minus 8 to the fourth, that, all right, y cubed became y to the fourth divided by 4. So that's minus 2 y to the fourth plus, we'll call this h of x. Okay, so once you've proven that it's exact, you can say, okay, now I know that the first one was the partial derivative with respect to x. Okay, so I can integrate that. But remember that when you did a partial derivative with respect to x, it is going to kill any element of a problem, which is just g of y. If it's just a function of y, and you take a derivative with respect to x, a partial derivative with respect to x, it sorry, somebody's trying to join the meeting in the middle of my recording. Okay. Okay. So what is this g of y right here? That's that. Right there. Okay. What is this h of x? This h of x right here is exactly this component right here. And then there's a common element between the two, which is the 4xy. Okay. So if I was going to write down the full solution, the full f of xy for this problem, I need to account for all of that. So the solution to this problem is going to be 5x squared divided by 2 plus 4xy minus 2y to the fourth, and that's going to equal some arbitrary constant. Okay. I want y'all to think about this. If I took the partial derivative with respect to x of this thing, first of all, this c goes to 0. Okay. So if I took the partial derivative with respect to x of this guy, which I'll pay attention to this. Crap, I'm not gonna be able to get it all the way off the screen. What's gonna happen is this term's gonna go away. Okay. If I took the partial derivative with respect to x, this term goes away. X goes away. That turns into x squared. And so what I end up with it's exactly 5x plus 4y. Okay. Now, if I took this thing and I took its derivative with respect to y, okay, what would I end up getting? All right, so this term would go to 0. If I took the derivative of this with respect to y, I would get that. Okay. All right, come down to this one right here. If I took the derivative of this with respect to y, what is it going to do? It's going to spit a 4 out to the front, turning that into an 8, and it's going to drop the exponent down by 1, so that it's 3. And that will give me that term, right? So this whole thing right here, this is actually the solution to the problem.